Hello, welcome back to our introduction to the C programming language. This is session number 4. Last time around we went over basic data types, qualifiers, storage classes, constants and strings, scope, and we differentiated between data initialization, declaration, and assignment. As promised last time, I do have some examples written up, so let me just Alt-Tab to those real quick. We have 3 files that we're going to be working with here. The main ones that we care about right this particular moment are main.c and static.c. And so let's go through this. In main.c, we see we have a lot of extern declarations of functions that exist elsewhere in the program. These 5 in particular, 4 of them exist in pointer.c, 1 of them exists in static.c, and there is another one in static.c that actually doesn't have a declaration. And we have an external declaration of an int stat int. These are all for demonstration purposes. In main, we call something called static main twice. And we have a couple of printf statements that are just dealing with printing values out to the screen. In static.c, we have int stat int equals 4. If I make this static, it means that this will exist for the entire life of the program. And it should be visible only to this file, but we will see about that. I'm learning a little bit here as much as you are, having played around with this a little bit. Static main has a static int scoped static, which can only be seen in static main. We print the value of scoped static, and we subtract 1 from it using the prefix ---- operator. And then there's getStatInt, which just returns the value of statInt here. So if I open my command line here, let's see if I can zoom in on it a little bit. Do gcc star.c, so that's every C file in this directory. If I ls here, you can see we have these there. We gcc star.c, we -o intro.exe. We have a warning here. Implicit declaration of static main, so we didn't tell the compiler that we'd be using static main, but it's technically valid, it just doesn't think it's very good practice. And we have a linker error here, undefined reference to statInt. That's interesting. So if we see in static.c, we have a static reference, we have a static definition of statInt here. See what happens if we remove the static here. This is still in the global scope, which means it'll still exist for the entire life of the program, but let's see what happens. So to run this again. This time that linker error goes away. So now we have external int stat int, and this works just fine. Run this, so /intro.exe, and we get the output we expect. So the first time we see static main is called, scoped static equals 7, and then we subtract 1 from it. We call it again, scoped static equals 6, proving that it still existed, it still referred to the same place in memory, and it actually got modified. Then we have the printout stat int lines, which works just fine here, and get stat int, which works just fine here. If we were to... Curious. Let's see what happens here. Here we go. Yeah, works just fine. So in this, we can see that at the global scope, static more or less restricts a variable from being seen outside of this file. And extern is more or less a reminder to the programmer that this is defined somewhere else, as much as it is a reminder to the compiler. Interesting little tidbit. With functions, calling them extern is implied. So if we try this, save it, clear, go back to the gcc command, Undefined reference to stat ints. You're right. I did the thing. You can see nothing changed. This is because functions are always visible in the global scope. But similarly, you can make a function static, if I recall correctly, and now it won't be able to be referenced outside of that file. So you can use static to hide things between files at the global scope, and you can use it in a function to maintain a variable outside of when it's normally supposed to go away. So with that determined, let's get back to work here. This time we're going to be going into the nitty-gritty of pointers, how pointers work. And that says user, not use. Oh well. Pointer arithmetic, how dynamic storage allocation works, the size of operator, and double and plural indirection. So, what are pointers and why do we use them in the first place? Pointers in C are used in a handful of different ways. We can use them to create dynamic data structures that can't all be contiguous in memory. We can use them to pass variables around to different functions. This is called passing them by reference, as opposed to making a copy of them and passing them by value. We can use them to access information stored in arrays. We saw this last time with the strchar and stir functions. And we can use them to reduce certain sources of overhead that results in our code being faster. It's a little difficult to describe how pointers work, but I will try the best I can here. If we have a variable int foo here, that foo refers to a space in memory that gets allocated for that variable. Whenever we use foo, we are just referring to that spot in memory and whatever is in it. A pointer is a variable whose value refers to some such variable or refers to some place in memory. On 64-bit architectures, pointers take up 8 bytes of memory. On 32-bit architectures, they take up 4 bytes. For larger, complex data types, it's often much faster to just copy a pointer to it and pass it along to a function than it is to create a whole copy of that data and pass it on to that function. And typically it's more useful too, because if you have a large data structure like that, in general you're going to want to keep it around and modify it directly instead of passing copies around and trying to use the assignment operator on it. So, how do we declare a pointer? What does it look like in our code? The way you declare a pointer is, it says here you have to put a star in front of the name of a variable. That is technically true, but not strictly speaking accurate. The star can go anywhere between the name of the data type and the name of the variable itself. So you can have int star space pointer a, you can have int space star pointer a, you can have int space star space pointer a, all of those are valid. Personally, the style I like to use is int star space pointer a, because the way it helps me keep track of it is the data type of pointer a is pointer to int. And having that all in one unit in the code helps me keep track of what's what. Different style guides will recommend different things, and different people will have different ways that they can remember what's what. The way that this is read is pointer A is a pointer to int, or pointer B is a pointer to void, which is a special case. This is often condensed or shortened into int pointer or void pointer. Void pointer is a special case, whereas int pointer specifically refers to a point in memory where an integer is stored. Void pointer refers to a point in memory where anything is stored. We cannot dereference void pointers, but we can pass them around and turn them into other kinds of pointers using casting. And we'll see an example of that later on in the scratch sheet. You can use the ampersand operator, which is the address of operator, in front of the name of an integer to get its address. We can see an example here. We have int x. We have pointer to int pointer underscore p. We assign 5 to x, and we just grab the address of x here. We don't do anything with them. Again, in later examples, we will actually do things with them, and it'll be interesting. We have an example of how pointer arithmetic works in this program. So, to get a quick overview, we declare a handful of variables, including pointers. So we have int var, int pointer, char var, char pointer, float val, and float pointer. Interesting that the naming convention changes here. We set int pointer to the address of int var, char pointer to the address of char var, and float pointer to the address of float val. We use printf to print their values as unsigned integers, and so we get them out over here. The numbers don't particularly matter because they're essentially random. They'll just be wherever there is free space in memory. We increment the pointers using the ++ postfix operator. And what this will demonstrate here is that pointer types are incremented according to the size of the data type they refer to in memory, which is why I told you all about that last time. So we see we have 2293300 here. After we increment it, we are at 2293304. We went up 4 bytes in memory despite only adding 1 to the pointer. The char pointer has a similar effect where we go from 2293299 to 2293300. We only increment by 1 because chars only take up 1 byte of memory. Floats being the same size as ints, we have the same increment here from 2293292 to 2293296 here. You can also add to pointers, which will produce similar effects. It is essentially adding a multiple of the size in memory of the data type to the pointer. So here we expect to gain 8 from last time, so that is correct here. We expect to gain 2 from last time for char pointer, correct. And we expect to gain 8 from last time on the float pointer, which is correct. So, pointers refer to locations in memory, but how do we work with what's actually stored there? That's kind of the important part here, no? This is what dereferencing is for. Putting a star before the name of a variable when you use it dereferences it, or depointerifies the value. We have the scratch work over here where we will actually show that. So this time we're going to set this aside, comment a few things out here. Uncomment pointer main. And let's go into what's actually in pointer.c. So there are 3 functions here that we care about. There is void increment, which takes in a integer by value, which means we get a copy of the value and not the same memory location. We add 1 to value and then we throw value away. We do nothing of use with it. Increment pointer takes in an integer pointer, so we get an int by reference. We dereference the ref, and we assign it to whatever is already there plus 1. So we get to see the dereference operator in use twice in one statement here. And then there is dump array, which I will use specifically later on. When we go into dynamic memory allocation, because one of the things that this function does is it allocates an array in memory, and then we fiddle with that array sum. So let's specifically focus on increment and increment pointer here. In pointer main, we create an int val equals 0. We create a pointer to val by taking the address of val, and then we try to run increment on val. As we mentioned last time, increment gets a copy of val here. So we add 1 to val and then throw it away forever. When we print out the value of val here, we expect to get 0. When we do the same thing, but we pass val by reference by passing a pointer to val, we expect to actually get 1 added to val. And when we print it out again, we'll see that that's true. And then finally, we call increment pointer by passing the straight up address of val instead of using a pointer variable for it. It's easy to remember that pointers are addresses and addresses are pointers. Then we print the value of val again, and we expect to get 2. Let's open up my terminal, clear it, recompile, gcc star.c-o intro.exe, run intro, and as you can see, we get the 0, 1, 2 we expect, and we get this output here, which I'll talk about what's going on there later. Back to the slide deck. Before we go any further here, we need to differentiate between stack memory versus heap memory, because we're about to go into dynamic allocation and the difference becomes important. Stack memory is a region of memory that the program and the C runtime will deal with on their automatically. Whenever you declare or define a variable, the memory for that is allocated automatically on the stack. Whenever you enter a new scope, meaning whenever you call a new function or go into a loop or an if statement, or just have a series of or if you just have a set of curly braces hanging out in your code, whenever you go into that, a new stack frame is created and pushed on the top of the stack. Whenever you leave that scope, that stack frame and anything in it is popped off the stack and lost forever. This is why lower scopes can see the variables of higher scopes, but not the other way around. When you're in a lower scope, all of the variables from the higher scope are actually still on the stack. They're just deeper in the stack. But when you're outside of that scope, there's nothing on the stack that represents those values. They just don't exist. They are pushed and popped off a stack data structure, so that is the last one in is the first one to get removed. And as mentioned, they are automatically managed by the C runtime. Heap memory is the alternative to stack memory. Heap memory is allocated dynamically at runtime. You have to ask your operating system for it. It's accessed exclusively by pointers to it, as opposed to the implicit references with named variables on the stack. And you have to borrow it from the operating system, which means when you're done with it, you have to give it back. And it's managed by the programmer in their code as opposed to automatically. So how do we manage that ourselves? We use dynamic allocation. One last quick note, the size of operator. Size of is very commonly used in the C programming language. I have an example of it on the scratch sheet. It is a compile time operator that is used to compute the size of whatever you pass to it. You can pass a variable to it, you can pass the name of a data type to it, and it will return a value, an unsigned integer, that represents the size of whatever you pass it in memory. This is how you can compute the size of larger data types. And it can be used on compound types like structures or unions, which we will go into later in the course. So, now that we know what size of does, how do we use that to dynamically allocate memory? There are two standard library functions that you need to know for this. They can be included using include stdlib.h or include standardlib.h. They are malloc and free. Malloc stands for memory allocation, and free is, well, free. Malloc takes in a single parameter, the size of the memory that you need. This can be assigned by you or computed, but ultimately what happens is the operating system will see if it has the memory available to give you, and if it does, it'll return a pointer to it in the form of a void pointer. If it doesn't, it will return null, all caps null, which is a pointer whose value is 0. The null pointer is always invalid, and if you try to dereference it, your program will crash. So whenever you malloc, it's important to check to see if you actually got it, if you actually got the memory you asked for. I think I actually forget to do that in the Scratch work, and I will correct that before we go into it. The free function takes the pointer that you return with malloc and deallocates the memory. You get no indication of whether this worked or not, but if you try to free the same region of memory twice, or if you try to free stack memory, or if you try to free memory that doesn't belong to you, your program will probably crash. If you do not free the memory that you get from malloc and calloc, the memory is lost when the program ends. This is what's called a memory leak. Memory leaks compound over time, and in the past, they would exist until you restarted your computer. Modern operating systems are a little better about dealing with them, but it's still not a good idea to just let memory leak out willy-nilly. Special tools like Valgrind exist to detect memory leaks in software you run with them. If we go back to the Scratch sheet here, you can see we have right here, int pointer array equals malloc 5, so we malloc 5 ints here. We get the result and we cast it to an int pointer. This is just to remind ourselves what we're doing with it. And as I suspected, I actually did forget. So if array equals null, printf, we didn't get the memory, exit -1. I think that ought to work. And so now, this should never actually run because, well, my machine has more than enough memory, but it is still good practice. So, let's go here. Solve the little errors, run intro, and see what happens. So let's look at the code and look at the output we got. We know what happens with this 0, 1, and 2, but why, when we call dump array, is there already a bunch of random values in here? When you allocate any kind of memory, but heap memory in particular, the memory is given to you as is. Whatever is already in there, the operating system and the C runtime don't do anything to change it. So when we call dump array the first time, we just get whatever we were handed. In these lines right here, we say array sub 0 equals 1, so we assign the first value of that array to 1, and we can also talk to that memory by dereferencing it and adding values to the pointer. So we assign to the memory we were given in 2 different ways. Called dump array again, and if we go back here, we see that we get the 1 and 2 where we expect them. The rest of the memory is still as is. Then we free our memory. Again, we get no indication of whether or not that worked, and we return 0 to exit cleanly. I mentioned that your program will crash if you try to free the same chunk of memory twice, so let's try that. Clear, go back to our GCC. Intro again. Huh, that's interesting. Should have crashed. I expected it to crash. I guess some runtimes can handle it and some can't. Do not bet on that behavior, ever. Let's see if this one can deal with having stack memory freed. So let's try to free val pointer. CC. Surprising, actually. In another environment I tested this on, the trying to do either of these actually crashed the program and caused what's called a segmentation fault, which is what happens when your program looks into memory it's not supposed to. And the way that works is the operating system allocates memory for its different processes and then keeps track of where each process tries to look. If the operating system doesn't care if you corrupt your own memory, but if you try to corrupt memory somewhere you're not supposed to be touching, then you are potentially endangering the processes that are running elsewhere on the operating system, and that's not okay. So what will happen is the operating system will stop your program's execution in order to maintain the validity of the data. Here's one that I am pretty sure will work. We try to free val itself, because remember, val's value is 2 at this point. So if we try to free the memory address 2, I expect bad things to happen. Pointer from integer without cast. Yeah, see, the compiler won't even let me do this without some shenanigans. Cast that to void pointer. Yeah, you see, the compiler really doesn't want me to do this, and I'm having to try to jump through hoops in order to even get it to work. In the interest of time, I encourage you to play around with this by yourself. So let's get back to business here. The last thing we really need to cover here is double indirection. We know that pointers can refer to places in memory, and they can refer to specific data types, but the pointers themselves are variables with locations in memory, and pointer itself is a data type. Specifically, we have pointer to int as a data type. You can have pointers to pointers, which allows you to have multiple levels of indirection, and you can actually extend this beyond just 2 levels of indirection if you really needed to. I can't think of a situation off the top of my head where you need it, but it is possible. You can have int pointer pointer pointer. In this example here, we have int I, we have int pointer, we have pointer to int pointer 1, and we have pointer to int pointer 2. This clear screen just empties the terminal screen. We say pointer 2 is equal to the address of I. So now pointer 2 refers to I. Pointer 1, which remember has that extra layer of indirection here, now refers to pointer 2. In this printf here, we get the value of whatever pointer 1 refers to at the bottom level. So we use the dereference operator twice, and we get the value we expect. That's 50, which is what's called an I. And in the second one, we just dereference pointer 2 the old-fashioned way and get that 50. On this slide, we actually have a diagram of how that works. So I has a chunk of memory assigned to it. That memory is at address 2000. And we hold 50 in that chunk of memory. Pointer 2 points at or refers to this chunk of memory here, and so we hold the value 2000 in pointer 2's chunk of memory. Pointer 2 exists at the address 3000. And pointer 1 does the same thing. It refers to this chunk of memory, and exists at the address 4000, holding the value 3000. Whenever you dereference a pointer, you actually just follow one of these arrows further down this chain. So pointer 2 gets dereferenced, and we get to I. Pointer 1 gets dereferenced, we get to pointer 2, which we can then again dereference to get to I. If you try to dereference I, you're going to have problems. Either the compiler will stop you, or if you do enough shenanigans that the compiler can't stop you, your program will just crash probably. Whenever I say a point, and again, if your program crashes, that's not a good thing if you try to publish it, but it is a good thing if you're trying to debug it, because it means that the operating system stopped you. It means that you've essentially gotten warning that you're doing something wrong before something actually went really wrong. So, in summary, we've gotten into the nitty-gritty of how pointers work. This is probably something you'll have to play with yourself, and something that you may want to reference the video on again while you're working with this. We've gone into dynamic memory allocation, how to stay safe when allocating your memory by using free, how memory is given to you, and how to manipulate pointers and essentially go frolicking around in memory. In the next session, we'll be going a lot deeper into how macros work, when to use macros in functions, how to inline common calculations, when to use a macro instead of a function, and how to debug using macros. As always, there are private coaching sessions available for software design and engineering and C and C++, among other things, on the website. Thank you for joining us.